So Jasmine asked about 37, and there's the shape in the center. Is that piece okay, or is it the standard deviation spread? Oh, you didn't have the data you needed. I gotcha. Okay, so for 37, it asks you to refer back to 35. I'll go ahead and let you get this written down, and then after we take our little notes today, we'll come up here and take a picture of the book so you can see where I got these numbers from, because I don't think the graphics are showing up like they should. So what happened in 35, they gave you a little setup, and they actually told you that the population distribution was normal. If they do that, you don't have to worry about the sample size or graphing or anything like that. You can assume that your sample is normal as well. So that makes it nice when they come out and tell you that. The center, remember we're talking about the difference between the means. So the center for this one, I just subtracted and got 18. Now the spread, I was thinking that y'all had asked that because the spread's a little bit more difficult to find. And this notation don't, talk about the standard deviation of the samples, so that's what that notation is. And the population had a standard deviation of 41, but remember, when we've got a sample size, we've got to divide it by the square root of that sample size, okay? Because the 25, the sample size of 25 is going to have a smaller standard deviation than the standard deviation of the population. That makes sense, okay? So we've got 41 over 25. I'll go ahead and put a minus there, and then we need to talk about it. Do you remember when we were talking about standard deviations? Standard deviations always do what? They accumulate. They always add. And we can't add standard deviations. We know we need to kind of add this some kind of way, but you can't add standard deviations because how do you get a standard deviation? You take the square root. So what do we have to do to be able to add these? We got to square it. We got to take it back to a variance, and then we'll undo that at the end. Well, if you want to do it all in one swoop, what you can do, and I got a number for this, okay? I did 41 divided by 5 and got 8.2. So I'm going to square that. Remember, plus, because variances add. 30 divided by 6 is 5. I'll square that. I could have made 2 steps out of this, but I squared it to take it back to a variance. I added it because, that accumulates, and I took the square root, and that gives me 9.6. And that's kind of why I thought y'all had used to do that. That's how you do that. Make sure this piece is okay, because I feel like that's going to come up again. Jasmine, is that okay, other than not being able to know what the number is? And then what about 45 did you need to say? 45 asks you to run a 90% confidence interval and then to interpret the 90% confidence interval. I'll tell you what, let's do this. Let's run the confidence interval together. 675 for males, 621 for females. information for males and females, and it has to do with summer jobs and how much is earned. And it says, looking at this data, how can you tell that it's strongly skewed to the right? So that was the A part. I thought that was actually a pretty good question. How do you know that that's strongly skewed to the right? The mean that the guys made was $1,884. The mean of the ladies was $1,360. And then there's your standard deviations for both. So how do you know this distribution is strongly skewed to the right? We don't have a graph or anything. We just have these summary statistics. But how could you tell from this that it's going to be skewed to the right? Think about it. Okay, so if we do males, they've got their mean there. And what's the lowest number that I can have here? We're talking about money you earned in the summer. Okay, so 0. Right, and the standard deviation is $1,368, right?
So you can like make like $1 million.
Yeah, but like even if we just go up, say $1,300, or if we go one Z-score to the right, 13, let's see, that would that give you about 3,300? I'm just guessing. Okay, and then if you go 1,300 this way, you're to 500, one Z-score, and then the standard deviation is so big on this, and since you can only go to 0, it makes sense that this thing's right skewed, because you're only looking at like 1 and not even a half of the Z-score this way. So this thing's gonna be really skewed to the right. And it's because that standard, look how big that standard deviation is. It's almost as big as the mean, and it's the same thing with the females. And since we can't have a negative summer earnings, you can tell it's really right skewed. So that's the A part. The B part, now let's actually run the test. It's a, and we're not going to panic it. We're just going to put the data in our calculator. So get your calculator out. We're going to stats, test, and we're doing a confidence interval, and there's 2 samples. So we're going to do a 2-sample t-interval. Of course, I haven't done parameters or assumptions or anything like that, but we're just going to run it for right now. Okay, did they give you data or did they give you stats? Awesome. I knew we didn't need that L1 and L2. Okay, so for the first mean, it is, we're going to make males our first one, 1884.52. The standard deviation on that is 1368.37, and our sample size was 675. Sample size is so big that it's okay to go ahead and do this even though it's skewed. If we hadn't had such a big sample size, we'd be having a different conversation, but since it's way over 30, we're in good shape. Okay, second mean, 1360.39. Standard deviation, 1,037.46. And cool, remember, in means, it's always no. Notice, just no. Just say no. 413. Something a little, no I didn't. I got exactly what it's looked at. I was going to say I got something a little different. Okay. So is everybody okay about putting this in your calculator now? So do you use two sample T interval? Yeah. Right here, but look, why not turn the lights out? When I did the calculators, if y'all remind me, I need a clapper where I can just clap for them. Yeah, see right here, it's a two sample T interval. Anybody have trouble getting those numbers? So, I got 413, 62, 634, 64. And we can interpret that, we're 90% confident that that captures the truth. What does that really mean though? Do we understand what that means?
Mm-hmm.
We're talking about the difference. So the true mean difference between what guys and girls earn is between that and that. I've got a note that C is very important because let's say we ran the test, we panicked, we concluded in context, and then it asks you to interpret what a 90% confidence interval means. And if you remember from the pre-response we just did on the mock, one of them asked you to pick out what the correct definition of a confidence interval was, and it was tough. I looked at it and I looked at the key and then I looked back and it was still tough to me. I didn't like any of them really, but they're going to ask you at some point to define what a confidence interval means. What does the fact that we got a 90% confidence interval that gave us those numbers mean? Does that mean black and white every time every kid in the summer that's a male is going to make, is that what that means? Okay, so can I kind of polish that up a little bit?
If you conducted the test many, many, many times.
Okay, okay, I'm going to repeat this. Repeated, okay? If we repeated many times,
90% of the time you can get that, right?
um,
I mean, I'm not saying it in like a super great way, but
repeated many times in the same way,
yeah, that's important detail.
about 90% of the intervals
All between those results, right?
nope, close though, would capture true actual difference in mean salaries. I probably did too. I haven't actually looked at that one on mine. I didn't like any of the choices, to be honest. I thought they were kind of on purpose, a little confusing. But anyhow, the whole point of a confidence interval, we're 90% sure that if we did this many, many, many times, about 90% of the time we'd capture the truth. So you got to get that in there some way. We would capture the true actual difference in mean salaries. So we're doing it a lot of times, and about 90% of those times we're going to capture the truth. So we're 90% confident. We did that many times, we captured the truth. So we're thinking the truth is in there. And zero's not in there. So that supports the idea that maybe there is a difference, Okay, so that's 45. And let's see, do we want to do something else? Yes, we do want to do something else. We're not going to take any notes. Since you already have your calculators out, I'm going to go to our notes, and then tomorrow we can just write it up, and you won't have to use the calculator. Okay, so no writing, just kind of thinking with your calculator. We've done 2 sample prop for confidence interval, 2 sample proportions for tests. We've done 2 sample means for confidence intervals. Now we're going to do 2 sample means for a test. It's followed the same pattern as what we did with the 1 sample. Okay, so now, we're gonna do a 2-sample t-test. Alright, and our 2 samples have to do with paper towels. We got 30 Bounty paper towels and 30 generic paper towels. And I will tell you, Bounty is better than generic, in my opinion. That's one thing I don't buy is generic paper towels. So we're gonna do 30 Bounty, 30 generic paper towels. We're gonna get them both wet and see how many quarters the Bounty will hold before ripping and how many quarters the generic will hold before it falls apart. Does that make sense? Okay, so they gave us some data. Turns out that the mean number of quarters that Bounty will hold is 117.6 with that standard deviation. The mean that the generic will hold is 88.1 quarters and that standard deviation. So we're going to use a significance test to determine if wet Bounty paper towels can hold more. So let me show you, and you don't have to write this, we're going to write it, but just so you have an idea of what we're looking at, the hoe is, remember hoe is always that they're equal, or you could put that their difference is equal to 0. I don't know which one you prefer. This makes more sense to me. Okay, but you could have wrote it like this. I'm going to do it in blue. Because those mean the same thing. And then your hot is that the Bounty will hold more than the generic, or if you like this method, you could say that when you subtract them, you're going to get greater than 0 because Bounty's bigger. You pick your hoe and hot. I like this one. That one's okay too. That one's just as good. Okay, so let's go to our calculator. We're going to go to stat. We want to go to test. And we want a 2-sample t-test. And we're going to input stats again. So X1 is 117.6. Standard deviation is 6.64. 30. Let's see. We're thinking that it's greater than, so I've got the wrong one highlighted. And we're going to say no to the one. I don't like the way they do their inequalities. To me, it's a little bit confusing, but I knew it was greater than, so I did. Okay. Did y'all get that? Did y'all get the same numbers I got? Your p-values. What is your p-value?
2.1.
And
0.
0. P-value is probability. Probability is always between 0 and 1. So if you ever put down a p-value greater than 1, go back and fix it. Yeah, it's a p-value 0. So what happens if p is low? Well, you do the hoe. You reject the hoe. P is low. So we're saying that there is evidence that Bounty will hold more quarters than generic when it's wet. And then tomorrow we won't have to calculate it. We'll just write it up.